Okay, hello. Welcome everybody to this Tech Talk. I've been a fan of Erlang for a little over a year now since the Silicon Valley. My name is John Brewer, by the way. I'm hosting the speech for Google. And I've been a fan of Erlang for a little over a year now since the Silicon Valley Patterns Reading Group did a segment on it when we were going through a lot of different programming languages last year. Obviously, as a Googler, one of the most interesting things to me is that Erlang seems like it offers some opportunities for efficient use of the new multi-core CPUs as we're getting up to between multi-core and hyper-threading. You could easily, in the few years, have machines with 100 concurrent CPU threads, and it would be nice to be able to use more than one of those. And so our speaker today is Mr. Lennart Ohman, and he's been working with Erlang since 1992, and one of the things he's worked on is the OTP, which is the Open Telephony Platform, which is basically a concurrency library for Erlang that provides some higher-level constructs. And he's currently managing director of the consultancy company Stjåland and Tiselius Telecom AB in Sweden, and happened to be in this neck of the woods scuba diving and was kind enough to come out today and do a tech talk on Erlang. So let's give him a big hand.
I'm happy to see so many of you here today. I thought actually it was going to be kind of a little audience of 10 people or something like that, and they were just going to videotape this, and just for the record, if someone wanted to see it. So I'm really happy to see so many people. Yes, thank you very much for the introduction. As you said, I've been working with Erlang since 1992, and yes, that's a very long time. I didn't think I would be still making a living out of this by now. So sometimes when I give classes, I say that if there's something you don't like in Erlang, and especially in OTP, there is a saying you should not kill the messenger, but in this case, it could be correct. I'm both messenger and responsible for some of this mess. Okay. When I was going to put together a little a paragraph about what this talk was going to be about, I thought, how long has Erlang existed? And then it struck me that we're actually celebrating our 20th year this year. And it seemed to have gone just secretly away. I guess that because most of the people who founded Erlang, started it, is no longer with Ericsson, and they're working for a lot of other companies. But I really have to take this back to Sweden and remind the Erlang community that we are actually having a celebration this year. It all started in the middle of the 80s at something called the Computer Science Laboratory in Stockholm, Sweden. I'm going to come back to some more interesting dates later in this presentation about Erlang. First, I'm going to go through the main design goals. Why did Ericsson decide to make yet another language, like we didn't have enough of them? First, when I came in contact with Erlang in 92, doing my master thesis, I kind of thought something like that. Well, cool, another language. Seems cool for a master thesis and doing something around that, but does the world really need another language? But working more and more and getting into the telecom sector, I realized that Erlang was actually pretty neat and pretty well designed for many of the problems, and that there was no real good solution somewhere else just to pick up. After I've gone through the design goals, I'm going to go into a few programming examples. That's why I was playing around with Emacs here. and try to demonstrate the major advantages with Erlang, and so you can see how it works. And then finally, I'm going to talk a little bit about the history so you can get a grip on the development and what's happening over these 2 decades. And finally, something about the future, where I think Erlang is heading. I don't know how these tech talks work. I like to have questions when I'm talking. I don't know if that's possible to manage, but that's at least fine with me. The worst thing which can happen is that I'm simply going to ignore you. That's because I'm feeling that, oh, if I stop now, I'm going to lose the thread, and then just try to ask the question again later. So, goals for Erlang. What was it the computer science laboratory discovered in the middle of the 80s? They actually set out to program PBX, an office switch, in, I think, over 20 different programming languages and/or development environment to see the strengths and the weaknesses for their problems. And after doing that for a year or 2 or something like that, that's when they came to the, of course, very interesting and very exciting decision that we're going to make ourselves a programming language. Not that we need to invent something new, perhaps, of course, a little bit new, but we've seen a lot of good things to have in various environments and programming languages, but we want them in one single programming language. Targets or goals they set up, or problems, I could say, they saw when they programmed this office switch was fault tolerance. In the telecom sector, downtimes of fractions of seconds per year is nearly acceptable. You have no time when you can take the system offline and plan maintenance. This goes hand in hand with the non-stop property. Of course, a system goes down if it breaks, if you have an error. And what shall we do? Write error-free software? Well, sometimes you actually, during my career, I hope this person will not see this talk. I've listened to presentations where quality managers have said, now it's very important that we write completely error-free software. And we from the Erlang department raised our hands and said, Mr. Manager, that's impossible. And like, what did you say? Impossible? But you are very skilled Ericsson engineers. You shall be able to write error-free software. Well, we all know that if you write a large enough system, you will have errors for one or the other reason, either because you make mistakes yourself or because you didn't understand the problem domain, or perhaps it wasn't properly described. So the only way is try to make something which is a little bit more understanding, and where a small error will not bring the entire system down. But non-stop is not only about errors, it's also about maintenance. Software needs from time to time to be upgraded. At least not because we actually discover errors. We discover them before they cause any major destruction. And well, we all know what happens when we've clicked the Windows take this upgrade option, and then after a couple of minutes the box, now you have to restart your computer, comes up. Not really acceptable. Other areas of the problem they investigated was actually concurrency. A telecom switch is heavily concurrent. I think that at that time, in the middle of the 80s, concurrency was more of a unknown or not that important property than it is today. Today, many people writing software today write softwares for internet shopping systems, online banking, and stuff like that. And then you can very easily picture, yes, I will have thousands, perhaps 100,000 of users simultaneously doing tasks which are more or less unrelated. And you see a concurrent world in front of you. But at that time, I think that computer systems was more about processing, to be a little bit mean, those punch cards and things. You have a single in-data stream. You process it, and you do something with the output, or you have a user doing something with the computer system. So concurrency was pretty new, or at least not really necessary. Therefore, it came up as, yes, we really need concurrency in our programming language if we are going to be able to describe typical telecom problems. And then, of course, not internet users, but instead people making phone calls. And of course, one phone call to another is unrelated to the other, your neighbor making a phone call to his grandma or something like that. Distribution, scalability, and heterogeneous networks. Once again, we go back to a time when it was not uncommon that if you bought a computer system from a vendor, you were kind of stuck. You had to continue buying their hardware to have a chance to get the equipment to talk to each other. The computer science laboratory said that, well, no, we don't think that's the future. We think the future will be networks of old computers, new computers, computers with this operating system, and computer with new operating systems, and things like that. So we need to target a heterogeneous network environment, and at the same time, we'll of course get a distributed environment which will be scalable. So we can start off with one single CPU and end up with multiple CPUs. Once again, we think back to what the telecom world looked like and still looks like. You have small customers and you have big customers. And there is usually a significant difference between a small customer and a big customer when it comes to an amount of equipment they need. And of course, you don't want to have to sell them completely new equipment when they grow and become a big customer. Soft real-time properties. Yes, the telecom world is soft real-time. It's real-time in the sense that you want your calls to go through. You want your online bookings, your online clicks, or whatever it is to go through when you are doing them. But it's not a complete disaster if you, from time to time, actually get some delays or actually fails. It's not hard real time like if you're controlling an aircraft or a spacecraft or something like that when people will die and a lot of money will be lost if the computer isn't doing some action precisely at the precise moment. Last but not least, prototypeability. I think I've invented my own English word here. At least a spell checker started to complain about it. The computer science laboratory saw a great advantage in having either a programming language or a tool or a development environment, name it whatever you like, where it's possible to start off very quickly with your idea. I want to do this. Let's try it and see what works and what doesn't work. Instead of us having to make a complete architecture and decide a lot of stuff before we can write one single line of code. And more importantly, before we can test our code and see if our ideas really works. So this was more or less the major points they ended up with after trying a lot of programming languages. This is what we want. And we can't find this in one single language or development environment. Yes, please.
I'm a little bit surprised that these are all design goals for a language. I would think that these are design goals for a system. Are you planning to say a little bit more about what properties a language must have for a system written in that language to have these properties?
Yes. The question is, aren't these goals for a system rather than for a programming language itself? I think I'm gonna dodge the question by saying that you need mechanisms and primitives provided to the general programmer or to the developers in order for a system to have these properties. Otherwise, they tend to get lost in the way. I don't know if that's an answer to your question. Please feel free to ask again if you see another slide where you think I could elaborate more on that. So if we dig into to these goals, how was this met in Erlang? Well, fault tolerance. Mainly, fault tolerance is about isolating the problems, the areas where we experience an error, to make sure that it doesn't spread and infect other areas. And mainly I would say this is done in Erlang, that the language has a lightweight process concept built into itself. When I give Erlang classes, I kind of say things like this. I don't want to see any Swiss Army knives, you know, big blade, the little scissors, the corkscrew, and stuff like that. Instead, you should make many processes. One for the corkscrew, one for the nail clipper, and so on. So if you have a nail clipper malfunction, if you've done it properly, only the people using the nail clipper at this time will experience some kind of disrupted service. And then it's very important that these processes are isolated from each other. And that's mainly how it's done in Erlang. It's also very cheap to spawn a new process. So there is really no reason to save on the processes. If you want to have 100,000 processes in Erlang, have 100,000 processes. If a process then terminates, of course, someone needs to do something about this. So there are mechanisms in Erlang for process supervision. And now we're actually touching a little bit on the topic of OTP. Erlang has a lot of nice mechanisms, but the OTP is a framework on how to use them in a consistent way, so that you do it in the same way in an entire application, and even better, do it in the same way in different applications, so that you may be able to borrow things back and forth. Non-stop mechanism then. Well, fault tolerance obviously is an important part in non-stop. We don't want to have service disruptions. But also hot code replacement is very important to do these upgrades. So Erlang has built into itself the possibility to have two versions of the same code at once, so you can make kind of a transition at a time when it's good, or it's good to you or to the application. Distribution and scalability then. Well, when it comes to the distribution mechanism, it is transparent when it comes to how processes works. The main mechanism, since I kind of gave the clue that it's very important that processes are independent of each other, that they are very isolated for an error not to spread to another process. Then, of course, how do we write programs? Well, we have a process passing, inter-process message passing mechanism. And by making this inter-process passing mechanism completely transparent to the distribution, we have a scalable system. So if you can find some way to break your world of processes apart and have, instead of having 100,000 here, you have a 50,000 over there and 50,000 here on another CPU, you do not have to change your code. In order to achieve distribution which is independent of what kind of platform you're using, Erlang uses a virtual machine then. So you compile your source code to a binary code, which is in the Erlang world called beam files. And then finally on this slide, which is actually new, SMP support. So if you have a multi-core processor, you can make your Erlang virtual machine run several threads, and these threads will pick Erlang processes, runnable Erlang processes from a run queue and start to run them. There are, of course, some situations where locking becomes too difficult. Internal locking mechanisms becomes too difficult, so that the virtual machine goes down to one thread. But that's very, very rare occasions. Code loading is, for instance, such an occasion. But that's something you only do at startup or when you need to do a hot code replacement. More about the scheduling or the processes, the concurrency. The process module the computer science laboratory found was the best one, was actually a very simple one. Instead of having priorities and functions and mechanisms like that, they found out that simple round-robin preemptive scheduling is what creates the least amount of problems in the applications. So, more or less, it's in a way that instructions in the Erlang program they have a price tag, and a process pays for executing Erlang instructions, and when it's out of pocket money, when it's out of its allowances, the scheduler takes the process out and, of course, takes the next one in the runnable queue. Another interesting thing is actually that all processes are equals. A lot of what's seen to the user as part of Erlang is actually Erlang processes themselves, and they are equals to other processes that you create yourself to run your application. Soft real-time. Well, since we have a virtual machine which takes care of memory management for us, hard real-time properties will be very, very difficult to achieve. But a lot of work was put in already from the beginning and is constantly put into fine-tuning memory management and garbage collection mechanisms in the Erlang virtual machine. So for the kind of soft real-time applications which Erlang was originally targeted for, and others alike, communications applications, the soft real-time properties are by far good enough. The prototypeability then. Well, the wizard has an idea and wants to try it out. Actually, from one of the things I've been working with is selling Erlang. That was before it was open source, before the big open source trend. Some people call it spreading the gospel. And one of the things we talked about, we leaned very heavily on, was actually what I now call prototypeability. We at that time called it time to market, which seemed like the buzzword of that era. We talked a lot about Erlang being a declarative programming language from the functional paradigm rather than imperative programming. And we stressed very much that this is something which makes you more productive and, of course, better time to market. Maybe as years has passed by, we in the Erlang community, actually inspired by a talk at MIT that Joe Armstrong, one of the original inventors of the programming language, gave. He talked about concurrent-oriented programming and got a lot of positive response. A lot of people said, okay, now I understand why you're using Erlang. And I and a lot of other of the peoples we were working with selling or talking about Erlang, we also actually got saw that, yes, we should have talked about concurrency-oriented programming, concurrent-oriented programming, rather than leaning so heavily on the functional paradigm of the programming language itself. Even though I still argue heavily that the declarative nature of the programming language is an important part of that you can actually very quickly sit down and get something done and test it. But from a strict computer scientific point of view, I would actually say that it's runtime linking. It's that you have the possibility to change one part of your system very quickly, just recompile it and enter it into your runtime system and try it again without having to go through a sometimes very tedious relinking process of your entire set of modules, code blocks, or whatever it's called in your development environment. And of course, the runtime linking comes back then to the hot code replacement features. So that was about the motivation and the goals for designing Erlang. Let's make a short crash course here so that you will understand some programs I'm going to show. Erlang programs are built up by functions. And not very surprisingly, very common in many programming languages. A function can be one or several clauses, and this is a function calculating the factorial value of something. And it basically works in a way that if I'm going to calculate factorial of 2, the runtime system first tries the first clause, which requires the argument to factorial to be exactly the integer 0. So it doesn't match, so we do not go into this clause. Fortunately, we have another clause, and here the argument is an unbound variable. Variables in Erlang are denoted by, you recognize them by the capital letter. They begin with a capital letter. So 2, if I'm calculating factorial of 2, n gets bound, 2 gets bound to n gets bound to 2 is probably the proper way to put it. And the result of factorial of 2 is 2 times factorial of 1 then. And then, of course, you recursively call the factorial function. And eventually, you will, in this call chain, end up in the first clause instead, because you are calling factorial with the argument 0, which will return 1. These functions are collected into, of course, Erlang source files. Such a source file is called a module, and a module is compiled before you can use it, and then you get a beam file. And these beam files are executed by processes in your virtual machine. So there is really no connection between Erlang modules and processes. They are, when I give classes, I usually explain it like Erlang modules are instructions, work instructions, and processes are people. Of course, many people can work out of the same instruction at the same time. I mentioned that processes communicate by sending messages. The messaging mechanism is an asynchronous messaging mechanism. So you as a process, you're allowed to send a message to any other process at any time you feel like. The process you're sending to can actually not protect itself. It will get the message. It's up to the receiving process what it wants to do with the message, if it looks at it at all. And now I am going to demonstrate some distribution, but since the resolution of this monitor or this projector doesn't seem to be very good, I think I'll prefer to just pull the code up in Emacs. So here we see a proper Erlang program. They start with the attribute minus module, where I say that this is the module test1. I have to export some functions that's basically APIs, functions that should be possible to be called from outside of this module. I have a start function taking an argument, and the start function calls a built-in function called spawn. This will cause new process to be created. It will be created at node, that is what I give as an argument to start, and that new process will start running the loop function found in the test1 module, and the loop function takes 0 arguments. That's why I have two hard brackets here with nothing in. So what will this new process do? Well, it will sit in a receive, and if a message comes in, that message will be picked up. This is what's called an unbound variable, so any message will match this variable. It will be bound to this variable, and I will go in here, and I will make a print out on the shell, Erlang display. I will print out actually my own process identifier. I just put it there so we can see who's talking and what message this process got. And when it's done that, it will simply make a tail recursive call back to the loop function. This is a very standard pattern of making a server serving requests. Now, of course, the messages this server will be expecting are probably a little bit more complicated than anything, and the services the server will provide are probably more complicated than just printing it on the screen. And there are probably several different messages which are recognized. But the principle is the same. You pick up a message, you serve the request, you make a tail recursive call back to the function where you sit waiting to pick up messages. All right. Yes?
Just a little more about what the node is.
A node is, I'm going to demonstrate it here, but I'll be happy to say it right now. A node is a virtual machine. So you can have one or several virtual machines running on the same physical CPU, or you can spread them out over different CPUs. I guess the later is the most common solution, of course. So now I am just going to call test. I'm going to pick the process identifier up. Test1 colon start. And this is actually a non-distributed node. This is an Erlang shell connected to a virtual machine. Just to demonstrate that the scalability property, I've chosen to have a non-distributed node. Yes?
That node function is built in?
Yes, it's a built-in function. I can run it here for you. Since this is not distributed, it's actually really silly. If you would ask me if I would have done this design decision, I would have chosen a value which would have been outside of the domain, the value domain of valid node names. So you can obviously not have a computer named no host and start an Erlang machine name it no node, because it would be very difficult to communicate with it. Okay. So I just simply start this here. And what's printed out there is the process identifier. And the reason why it's printed out is actually because it's the return value from the start function. The last thing done in a function is the return value. And since I call the start function in this shell, the shell prints out the return value. So now I have a process identifier. I can send something to hello. And then we see this is a tuple, and as I mentioned earlier in the code, I was going to get the process identifier of who was talking and the message it's got. And this hello here is actually printed by the shell because the return value of this message sending is the message itself. So therefore, I cannot make that go away. And of course, if I send something more, it will be printed out. Very good. Now let's start some distributed Erlang. Let's start a node here. This was actually a surprise. I got the same font as I've already set the others up with. But can I just get a little corner there and it's down? And this was bar, and then let's see if we have foo. First of all, I must there's a little security mechanism. I must set the same cookie at both nodes for them to be allowed to talk to each other. Kaka, that's cookie in Swedish. net add column ping. I can see if I can reach foo at J21R Pong. Very good. Okay. I must also actually move column data doc
No less.
You remember? We can always do it like this. Yes, you are right. Document projects Erlang presentations and Google 2007. And see if we can see if it wants to play. All right. Really doesn't matter which one we choose. So now we want to do a test one start, and I want to start this on the other node, foo at J21R. And I should have picked up the process identifier, but we can start another one. And then I send something over, hello, and we get it printed out. And I'm running the same code. So what I'm trying to convince you is that there is no big work involved in when you are scaling your software up.
Can you kill node 43?
You want me to kill the process I don't need?
Or not?
Well, as I said earlier, processes are cheap, so we can have them laying around. There's really no problem. They don't take up much space. All right. Let's get back to this slideshow. I think since I'm not going to... I'm going to demonstrate hot code change as well. And I'm going to do that in the Emacs, so don't bother with that you don't see what's written there. We take up the Emacs, and we check out the file test2. And here I modified this program a little bit. I entered one more clause in this receive statement. And this is, perhaps it's difficult to see, but this is a lowercase s. So this is receiving actually precisely what's called an atom switch. And what I make here is that I make a tail recursive call to the loop function, but you see that I have specified the module as well. What this actually means is that if I make a call to a module and if I make a call to a function in a module and specify the module name, I tell Erlang that I want to use the latest version of this module. And now you probably start thinking, okay, so that's how code change can be done. I can here continue to use this version, even if it's the latest or if it's an old version, whereas I here force the process to use the latest version. So if we bring our, if we bring this up again. And we this time we P1 we start. And I send hello again. Okay, hello comes out. Now we want to make a modification to this code. So let's say that we want to put in that if we actually get the message hello, we get hi back instead. And then, of course, we make a call to loop. Now we're going to do something interesting. Now I'm going to compile it in yet a third emulator. So now I have the code compiled, but not loaded. So we still get the hello here. If I now load test 2, now I loaded the new version. Let's see what happens if I now send hello. Still got hello. How come? Well, I haven't made the process change the code yet. So I need to send this switch message and then send the hello. Then I got the hi. Fantastic. Question in the back.
Can you console if you forgot to add something with switches?
If I forgot to...
If you forgot to add the clause that switches to the new code,
Yes.
do a hotspot?
The question is, what if I didn't have this clause, the switch clause from the beginning? Could I have pulled this stunt off then? No. Because if I would have only have had what's called local calls to loop, I would have had to start a completely new process with the new code. Maybe that's doable also. Maybe you can find some way to migrate data which this process is currently holding. But now we're yet again touching a little bit about OTP, that if you're using OTP, you get in the framework, someone has thought of this already for you so that you won't miss it. Yes?
Do all the distributed virtual machines have to share a common file system?
No, not necessarily. Oh, sorry. The question was, does all the virtual machines have to share a common file system? No, you can actually push the code out over the distributed network. So if one of those nodes didn't have the test2 module, I could have first loaded it from a node which has it, and then, of course, start running it there. All right, I'm running a little bit behind, as usual, I guess. So I want to just quickly finish off with where we're going right now, and I'm happy to take questions offline as well if we're out of time. From current slide. Yes, the OTP framework. I'm not going to talk about this here, but it has generic modules where typically this receive statement resides, making sure that you will not miss programming the switch message and things like that. And this generic module simply makes calls to a callback module where you have implemented the specifics of this process. A little brief about the history. As I already said, Erlang, the first experiments with Erlang started in 1987. The first project with Erlang started in the beginning of the 90s at Ericsson. And other milestones, late 89, Erlang OTP was released as open source. In 2003, the Erlang workshop became an official part of ACM SIG plan for functional programming languages. It alternates between North America and Europe. This year it will be in Germany. Last year it was in Portland, Oregon. We actually had our 10th Erlang user conference and that one is annually held in Stockholm in 2004. And another important milestone, I think, is actually the SMP support, which was rolled out last year. A bit of caution, it is actually not released for Windows yet. It will come soon. I don't know the exact release plan by heart. Some major usage. Ericsson. Yes. Ericsson developed an ATM switch in Erlang. Ericsson's SGSN GPRS node is developed in the control logic is developed in Erlang. Ericsson is right now developing some new products. One session border gateway based on Erlang. The Telia, which is the former Swedish PTT, which were actually jointly owning this company LMTel together with Ericsson, where Erlang was born, are using Erlang in a call center solution. And there are some other companies using Erlang. There are a lot more than these slides. These are the usual suspects we are allowed to talk about. There is a gentleman sitting in the audience which is programming Erlang for another company as well. So the usage, it's definitely picking up as we can see it. We see it also when we get to the statistics for the Erlang.org page, that we are now growing up to you are probably laughing, but I don't. How many hits does Google have each second? These are hits then per month. 1.5 million hits, or requests, more precisely, not hits, requests. But I at least like the trend. Currently, the development is still taking place at Ericsson in Stockholm. It's headed by its manager, Kenneth Lundin. And the story is that if someone wants to contribute something, you contribute it to the OTP team at Ericsson, which decides on the usefulness and the quality of the contribution and whether to include it. So there is no difference between the open source Erlang and the Erlang that's used inside Ericsson, for instance. For more information, I recommend erlang.org, or a brand new Erlang book, which is written by, yet again, Joe Armstrong, one of the initial inventors of the Erlang programming language. It is, the rumors are that it's actually available in hard copy sometime this week. Previously, it's only been available as a PDF. Well, I only missed the deadline by 2 minutes. Thank you very much for listening.